All right, so starting off with today, we're going to be talking about electrical potential energy. Uh, so before I get into that, though, let's start by talking about gravitational potential energy. So I have Earth here, and I have Flipbox evidently. So I've got Earth there, and let's say we know that things are gravitationally attracted to Earth. We kind of have a gravitational field that essentially is pulling things in towards Earth. Okay. I know my arrows aren't all the same size, but the big thing though is like if I have a rather large satellite here, actually a decent looking satellite, okay. I know that there's some gravitational potential energy here. You know, the satellite has the potential to fall to Earth. And so to figure out um, the gravitational potential energy, I just take the mass of the satellite times the acceleration due to gravity times the height, okay? The height there, okay? And I could figure out what's the gravitational potential energy of the Earth there. Uh, so just know, like, because of this field, this gravitational field, and where the satellite is in the field, it has some potential energy to fall. So let me go back. Try to erase what I did there. If I kept my arrows going the right way. All right. So now, electrical potential energy. All right. So I've got two plates here. Uh, and I have one plate is positive, the other plate is negative. So I know there is an electric field that exists between these two things. And the electric field lines we know go from, let's see if I get this right, from the positive to the negative, okay? I'm going to leave myself a little bit of a gap just so I can draw something else, okay? So they're going to go from, the electric field lines are from the positive to the negative. And I know that if I have a charged molecule here, let's even say that it's a positive charged molecule, and I want to actually push, this molecule, this positive charged, it could be an oil droplet probably, it could be something solid, but let's say that I wanted to move it, so this exists in a certain electric field, my charge has a charge of Q, and I want to move it a certain distance, I know that that's going to increase the potential energy, because essentially if I just dropped my charge here, my positive charge there, it's going to move that way. It's going to move with the field away from the positive towards the negative, okay? But in this case, I'm not talking about that. I'm actually moving a positive charge closer to the positive plate up here. So I'm going to increase my electrical potential energy, because essentially once I move this positive charge up this way, you know, if I let it go, it's gonna move back down towards the negative plate. So the equation we're going to use to figure out really the electrical potential energy, the equation we're going to use is negative Q E D. All right, so to figure out what the potential energy is, and specifically what the change in potential energy is, it's negative whatever my charge is times whatever the value for the electric field is. And keep in mind, this is for a uniform electric field. Uh, so if the plates are close enough together, we can assume the whole electric field's positive, not positive, but uniform. And we're going to take it times the change or the distance the charge moved or the change in x, you know, just typically we're just going to leave it d, okay? And the reason why that works, why we do it negative, is because I know that I have to do work to move that. Essentially, the work done on that charge is just equal to positive QED. But for the most part, we don't care too much about the work that we're doing. We're talking what's going to be way more useful is this change in potential energy for that charge. So we have, so pretty much that equation, it's useful, but less useful than this equation we're going to use right here. All right. So I've got a practice problem there that we're going to work with. So let me go down. Essentially what we're doing is, so with this problem, a charged oil droplet gains 1.9 times 10 to the negative 19th joules. All right, joules there, I know I'm talking about energy, electrical potential energy, while moving 3 centimeters in a uniform electric field. What is the charge on the droplet if the strength of the electric field is 2 times 10 to the fourth Newton Coulomb? All right, so what I know here is I know that the change in electrical potential energy is 1.9 times 10 to the negative 19th joules. I'm moving my charge 3 centimeters. And so if I want to put that, uh, I don't use centimeters in this equation, I use meters, just like we've been doing. And so that would be 0.03 meters. And I know that the electric field has a uniform strength of 2 times 10 to the fourth newtons per coulomb. All right. So the only thing I'm missing now is the charge, and that's actually what the question's asking for. So let me go ahead and let's plug in some numbers quick. So I have the change in potential of the electrical potential energy. I'm just going to pop it in parentheses right away. 1.9 times 10 to the negative 19th joules is equal to negative Q. Q is what I'm looking for, so I leave a Q, times the electric field, which is 2 times 10 to the fourth newtons per coulomb, times the change in distance, and we're trying to move this charge 3 centimeters or 0.03 meters. All right, so essentially I just need to solve for Q there. We could start just by multiplying both sides by -1, so I'm ending up with that. I'm even going to scroll down at this point. So in this case, so that takes care of the negative. I'm going to divide both sides by 2.0 times 10 to the fourth. It's coulombs, and by 0.03 meters. Cancels. Okay, so we're good there. And over here I've got 2.0 times 10 to the fourth newtons per coulomb, 0.03 meters. All right, so now I know newtons is like kilograms, meters per second squared. My units are all going to end out so that I'm going to end up with C up on top here. All right, so now Q is equal to negative 1.9 times, just kind of clean up the math I'm going to do here a little bit. This way you can, and I'm going to plug it into a calculator here quickly, but, well, soon, probably not quickly. If you've seen the other videos, you know how well I do that. All right, so now this is the math I'm even going to plug in. Just kind of make it a little bit easier. I'm even going to put the bottom part in brackets because I believe I've been having some PEMDAS issues lately. Order of operations stuff. All right. This negative, I'm just going to distribute into there. So parentheses 1.9 negative times 10 raised to the 19th negative, close parentheses, divided by parentheses, 2.0 times 10 raised to the fourth, close parentheses, times 0.03, close parentheses, equals, looks like my answer is going to be negative 3.17 times 10 to the negative 22nd. So let's go negative 3.17 times 10 to the negative 22nd. And once again, that was in coulombs. All right, so really, this isn't a huge change in electrical potential energy. I mean, we are moving it quite a ways because this charge, it's relatively close-ish to like the charge on like a proton or an electron or something. Uh, so I got negative 19 here minus another like 3, probably just kind of intuitively figuring out if this is the right answer. So negative 19 minus 3, yeah, negative 22. Yeah, that answer seems reasonable. Okay, so based upon this small change in electrical energy, electrical potential energy, even though we are moving it quite a ways, uh, that does give us a pretty small charge, pretty small strength of the charge there. Okay, and that's just the potential energy change when we move it, 3 centimeters towards the positive plate. Or, doing that once again, we know how much work is done to do that, and even then we could go back through and use like force equals force times distance. We now know the work that we did. If I just make that a positive, I know how much work I did. I know the distance I moved. I can actually go through and figure out, how much force was applied to move it that way. Really though, electrical potential energy, pretty basic, pretty easy. I actually like that equation just because it is nice and clean and neat. But yeah, so good luck with the practice problems.